afternoon. Our speaker today is Matthew Zimmerman. Since the founding of FarSounder in 2001, Matthew has driven the technological development and vision of FarSounder's 3D forward-looking sonar technology. His motivation of decreasing the environmental impact of all types of ships led to a new class of navigation products which enable yachts, research vessels, cruise ships, and other exploration vessels to access the most exclusive location with increased navigation safety. He currently serves as a CEO of FarSounder and is a member of the IHO's crowd-sourced bathymetry working group. I hope you guys enjoy it, and all yours, Matthew. Go ahead.
Thank you very much. First of all, thank you for having me, and I apologize that I'm not able to join you there in person. Unfortunately, I've had a very full travel schedule and just couldn't add another day out of the office. Anyway, thank you for joining me today, those of you sort of live in the online. So, as I was introduced, my name is Matthew Zimmerman, and I am one of the founders of FarSounder. And later this month, we celebrate 23 years since founding the company. And we've been shipping our products around the world to a variety of vessel types since 2005. And today, I'm going to be talking about how our technology applies to uncrewed surface vessels and the applications that they have. So, as I'm sure many of you know, over the past decade, we've really seen the rapid development of USV capabilities and applications. But the USV uses really started in fairly well-known areas that were well-charted. These were places where the operators were not concerned about unknown underwater hazards. And primarily the development of these vehicles were focused on how to follow the coal rigs and avoid collisions with other vessels using sensors above the water. But now that capability, I'm hesitant to say is fully matured, but certainly well developed. And there are a lot of USV applications that are now looking to push beyond these, quote, safe navigation areas into much more of the real world. And as many of you know, there at UNH CCOM, you have some pretty cool vehicles that are continuing to push the envelope on capabilities. So as the USV world gets into these new applications, worrying about navigation hazards under the water certainly becomes something that is much more of a concern. So in high latitudes, that's avoiding ice. In many of the high latitudes, there's little to no real chart coverage. From a security point of view, patrolling austere ports, there could be not a lot of chart information in those areas, or there could be new hazards that have been deployed since the last opportunity of charting and mapping those areas. Other applications include ship-to-shore pathfinding, and of course, MCM applications from the security point of view, which is starting to become a really big deal, particularly in light of the war in Ukraine. So all of these use cases really require a better understanding of what's underwater ahead of the vessel. And that's exactly where forward-looking sonar can play a role. So the first question is really, why 3D sonar? Clearly, when you don't have crew on board, you have significantly reduced situational awareness. As I'm sure many of you know, you can't rely on ENCs everywhere, and the traditional sensors that are operating above the water won't see anything below the water. So your down-looking echo sounder is not going to see that rock ahead. Your above water sensors, the camera, the radar, again, will not see that rock ahead. And if you take a traditional 2D multi-beam or a scanning sonar and simply face it forward, it's going to be pretty hard to also detect that pile of rocks. So to be an effective navigation tool, the forward-looking sonar really must have a wide field of view with a fast update rate and be capable of sensing from the sea surface all the way down to the seafloor with a single ping. And that's exactly what FarSounder's technology can do. So here's a basic little video of what type of information our systems can provide. Our products produce a 3D image ahead of the vessel at navigationally significant ranges with a single ping. And everything inside that pie wedge is real time ahead of the vessel, but we also build a map of everywhere we've been, and I'll talk more about that in just a few moments. Our customers are using these all over the world to avoid a wide range of hazards, things like coral rocks and sea bottoms, ice when navigating in polar areas, large whales, rocky pinnacles, shipping containers when they fall overboard from cargo vessels, and other unknown obstacles that are just at or below the sea surface. So we combine all of that information into an easy to use user interface, and we really focused on how to make our forward-looking sonar information clear, easy to use, and quick to understand. This is a screenshot video of our actual software with real sonar data. This is actually approaching the Newport Bridge in the Narragansett Bay here in Rhode Island. And on the left side of the screen, we see a full 3D view. The user can actually click and drag to rotate that perspective. And on the right-hand side, we show the same sonar information with a chart overlay. The chart overlay makes it really easy to understand and recognize what those sonar targets are. In this case, we're seeing some blips that correspond to the bridge pilings from the Newport Bridge. With the chart overlay, it's really easy to see that they correspond to known features. The important part about the chart overlay is it lets the operator very quickly understand where they can rely on the chart and where they can't, because when there's something in the sonar that's not shown on the chart, that's where you really want to pay attention. But of course, this is a user interface, and we're talking about uncrewed vehicles. So in some cases, when there's a human in the loop or remote control, this user interface still becomes really valuable. But for the autonomous or semi-autonomous operations, a machine interface is really more important than that human interface. And all of our systems come with a machine interface built in. It's available over the network, and it's basically giving you access to all of the 3D information that goes into our user interface display. Our software, which we call SonarSoft, runs on a PC, and it provides all of the sonar processing to create our images, the user interface display when appropriate, and also a network interface basically acting as a server. So we have an API that we publish and make available to our users. If you want to dig a little bit into the technical details, basically it's running on a TCP connection. We use protobuf for the packet formatting and 0MQ for the transport layer. And that allows us to expand other functionalities and interface into third-party systems pretty easily. If there's anyone interested in more details about the machine interface, I'd be happy to talk about that offline, and you can find a lot more details about that on our website as well. So I want to take a few minutes to dig into the physics and the little more of the details of what's going on inside a 3D sonar. So what we did here is we took one ping from one of our sonars where we were approaching a large commercial pier with a solid wall. This is where the car ships bring in their new cargo of new cars to Rhode Island. And we processed a single ping on the left side with traditional 2D processing. So essentially beamforming, horizontal angle versus time, so essentially range, with color mapped to signal strength. And we can see that there's a bright feature right along that white line, that dotted line, and that's where the pier wall was. And clearly there's bright reflections. But if you notice off to the left of that line, there are a number of other bright reflections. And what is that? In the 3D view, which we see on the right-hand side, processing that same ping with both vertical and horizontal angles simultaneously, we can see that there's depth information associated with those reflections. The right-hand side picture, though, is really complicated to understand and clearly not something that is user-friendly. So we have some further stage processing that essentially extracts the relevant information from that dense set of data to provide the pictures that we produce in our user interface. And this is the same process data that's available through that machine interface. Using this process data, obviously for the human operator, makes it easy to understand. But for the vehicle control system, having fully processed sonar data is really important because it no longer requires the vehicle control system to be processing sonar raw data. We don't see vehicles processing raw radar data. We don't see vehicles processing raw signals coming in from GPS satellites. They're using a processed GPS location, processed radar image, and we provide the same thing with the processed sonar. So getting back to that question of what were those bright things to the left of that dotted line, well, we believe it's an area of the seabed that is slightly harder, sandy bottom. This is where car ships come in, as I mentioned. The water depth is about 10 meters deep, and the draft of these car ships are 7 to 8 meters deep, and they have huge props. And it's a very soft, silty bottom covering some sand. So having actually done scuba diving in that area, I've seen small divots where that soft silt is washed away from the prop wash, exposing that harder sand. And my belief is that is the louder reflectivity, the louder backscatter from those harder sandy patches rather than the soft silty areas. So getting back to the 3D nature of our technology, I want to talk about some metrics. And most important metric is really range. Our products operate out to a maximum range at which we can detect things in general, but they can also map the seafloor in 3 dimensions. And that bottom mapping range is limited to a function of how deep the water is below the sonar. And this limit is a pretty easy thing to understand once you start to think about the physics involved. If you have a down-looking sonar, then pretty much all of your energy reflects off the seafloor back to you as backscatter. But if you push that energy forward at a steep angle, some of that energy reflects forward, most reflects back to you. At shallower angles, you have more energy reflecting forward until eventually you're at a shallow enough angle that all of the energy reflects off the seafloor, but it reflects forward as forward scatter rather than back scatter. And it turns out that that angle is about 8 to 1. So about 8 times the depth below the sonar is where our systems transition from backscatter mode to a forward scattering mode. And we're able to map the seafloor out to at least 8 times the depth below the transducer. Many cases we do much better, but of course we like to underpromise and overdeliver rather than the other way around. However, if there is a target that is at or beyond that bottom mapping range, we now have an edge that's able to reflect back to us, such as this rocky pile here. The result of that is in our software, we see both the 3D seafloor visible inside that pie wedge, in this case out to about 10 water depth, so doing a little better than what we specify, as well as a series of in-water targets that we see here nicely in the chart overlay. When those targets are within our bottom mapping range, we can give you a depth estimate of how deep those objects are. In this case, it's the bridge pilings. So they're going from the sea floor all the way up to the sea surface. And for targets beyond that bottom mapping range, we can't really give you a good estimate of their depth, but we can tell you the range and the bearing and how loud a reflector they are. In our software, everything that's within that bottom mapping range is color mapped to depth, where blue is deep and yellow shallow, and that's defined by the color scale on the bottom right-hand side of our software. Everything beyond that bottom mapping range is color mapped to reflectivity, and that's designated by the color scale at the top right of our software. And of course, we can also display the entire image as color mapped to signal level just by clicking a button inside the software. So some of you might ask, well, why can't we understand the depth of these targets beyond that bottom mapping range? And so I want to talk a little bit about that and why that is. When we get beyond that bottom mapping range, we're now in a scenario where the sound waves are bouncing off the sea floor, probably also off the sea surface, maybe both, maybe more than once. And this area is often referred to as the multipath domain because the sound waves have multiple paths they're bouncing off the seafloor and sea surface. Again, when you have an object sitting on the seafloor, in the water column, or extending down below the surface, you now have edges that will reflect that back to you. And whether it's reflections coming off of one or more bounces, it is going to come back to the sonar at some point. If we knew the complete propagation environment by understanding the sound speed profile, we could do a pretty good job of estimating the depths and unwrapping these reflections in the multipath domain. However, in this case, we are a forward-looking sonar, so we haven't yet measured or what's in front of us, so we don't have the accurate sound speed profile of what is ahead of the vessel, ahead of the sonar. And so in our systems, we don't try to unwrap that. We just provide range, bearing, and reflectivity. And as a result, when you look at our software, even at pretty long ranges, 1,000 meters range in fairly shallow water, we get good bottom mapping out to the 8 water depths or more, and reflections from obstacles out to the full range of the sonar. In this example, we're showing the shoreline, and we're getting reflections from the shoaling shore, the rocks right at the shoreline, the breaking waves, their bubbles, whatever it is, it clearly matches what's on the chart and gives the user a good feeling that they can trust the charts in this area because sonar is matching the chart. There's nothing extra there. There's no hidden obstacles in this location. FarSounder has 3 different product models: the Argos 1000, Argos 500, and Argos 350. They all have the same inboard equipment and the same software. We've cleverly named them based on their maximum detection ranges of 350 meters, 500 meters, and 1,000 meters ahead of the vessel. So that's more than 1,000 feet ahead, a little more than a quarter nautical mile, and a little more than a half nautical mile from our product range. Aside from the chart overlay basics that we talked about, we have a few other innovative features that are pretty valuable for both crewed and uncrewed surface vessels. I mentioned that everything inside the pie wedge is real time, but we also build a map of everywhere we go. We call this our local history map, and notice I'm calling this a map and not a survey. It's not quite a hydrographic survey grade down-looking multi-beam, but it's pretty good. And in many applications, the map we're able to build is good enough for those users. So whether it's returning to an area that you haven't been to before, exiting back through a treacherous passage that you mapped on the way in, or as we show on the right-hand side, building a short survey of an area where you're going to anchor before dropping the hook, you can do that survey, build the map, and then as the vessel is swaying with the tides and the currents and the wind, you can see where the stern of the vessel is relative to any shallows that have been mapped. We do have functionality through that same network interface, that machine interface, to export our data in real time directly into the QPS ecosystem via their Kinsey survey acquisition software. And you can use our data analogous to how you'd use any traditional down-looking 2D multi-beam inside the QPS ecosystem. In addition to the sonar overlays on the chart, we also provide AIS information. And in this example, we are passing by the previous path of another vessel. We can see the vessel crossing to the left of our sonar field of view, and they've left a whole bunch of bubbles from their wake. And turns out bubbles are great sonar targets. So having the AIS overlay lets the operator very quickly correlate, hey, these aren't obstacles, this is bubbles from a passing vessel. Equally important when looking at uncrewed systems, having that AIS information to compare the multiple sensors and get a good understanding for making navigation decisions. Similar to AIS, our software also supports ARPA overlays operating in a similar manner. So I mentioned a moment before that we build a chart, a map of everywhere we go. Well, that's also important for USVs when they're operating in a swarm configuration. Today, we build that local history map. It lives on the local FarSounder computer, and with an internet connection, we can actually share that map through a cloud service that we recently launched, and then download the aggregate map from all the other vessels. So in a civilian application, this works really nicely. We have a cloud service that we host and operate. Obviously, for military applications, many of them may not be so keen about having a public cloud service requiring public internet access. In this case, we envision migrating our current capabilities in the public cloud domain to a private server that could be running inside a private network operating by that swarm force. Again, how we do that is pretty straightforward. It's essentially a service, or set of services that we run in the cloud. Right now, we're using the Google platform. However, it's fairly platform agnostic, and we could migrate to other platforms. One of the really nice things about this cloud service is getting access to the aggregate map from all the other FarSounder users serves as an incentive for our users to contribute measurements. And then from our cloud service, we anonymously make contributions directly to the NOAA-operated DCDB, which is the crowdsourced bathymetry database for the IHO. And all of that information goes into CBED 2030, which is really a pretty great example of a global hydrospatial initiative. And for those of you that are not familiar with it, it's basically an effort to map our world's oceans by 2030. We're never going to get there by 2030, but it serves as a great rallying cry to help get the community to do that. And crowdsourced measurements is one component of the data that goes into the overall CBED 2030 initiative. So our customers get access to the highest resolution map data from our aggregate user base, and we contribute on their behalf anonymously a slightly lower resolution contribution to the DCDB. Everything in that DCDB is publicly available for free to anyone around the world. And we've made the distinction in these two levels of resolution so that our customers have an incentive to participate. Otherwise, they could just mooch off of everyone else accessing it freely through the DCDB. But we have committed to making contributions at least 100-meter resolution, which is the highest resolution requirement for the CBED 2030 initiative. As part of this fleet sharing effort, we've built a web-based sort of status panel that we use internally as a dashboard to see where customers and vessels are contributing, and we can use that for sort of quality control of the data as it's coming through our servers. And this is something that we're actively in the process of actually making publicly available through some partners that we work with, one of which is International Seakeeper Society, which is a nonprofit based in the US who works to connect research scientists looking for ship time with yachts all around the world to host scientists, deploy sensors, and make measurements. And they've been providing a number of their yacht participants with a simple echo sounder logging tool. So we're going to be using this web interface for them so they can help show their participants where their participants are contributing and how they compare to the others in the DCDB. Of course, higher quality crowdsourced bathymetry could be used for other USV operators. And so our model of letting the aggregate map come back to the participants is still directly valid for the USV configuration. And some of you might ask, like, why do we need CSB data? Where could it be used for? Well, one example is enabling hydrographic offices to produce new products of new charts. Here's an example that the Canadian Hydrographic Service released about a year and a half ago. They were trying to update their charts in the Northwest Passage in an area that had really close to zero official data, but they were able to find some, quote, trusted contributors from the community and produce a chart with community contributions. And some of those contributions actually came from a FarSounder customer. Our customers have very high quality meta data, which is essentially where are the sensors located relative to the GPS antenna and the sea surface and the vessel parameters. And that allowed the CHS to calculate the total error from the FarSounder users' contributions and found that this error fit within their error budget and therefore were able to include that in their chart management and chart generation. For other hydrographic services that don't want to rely on community contributions to be part of their official chart data, they can use them to help identify where there are locations that are in need of new surveys or updated charting. And I'm sure many of you know a whole lot more about that than I do based on all the activities at CCOM. In addition to looking for the seafloor and mapping the seafloor, some of our customers are using our equipment for detecting and avoiding marine mammals. Last fall, I had the opportunity to spend about a week and a half through various projects off the coast of Massachusetts, essentially doing whale watching, collecting data with humpback whales. We, of course, had PSOs on board and strict rules for operations on board the vessel and how we engaged around these animals to ensure that we were following all of the federal guidelines on operating in and around areas with marine mammals. And we went through the full NOAA guidance on acoustic harassment calculations to show that our equipment, when operating at appropriate vessel ranges, has no capability to harass marine mammals. But what was really exciting is operating these conditions, we were able to detect humpback whales out to 500 meters range, which was the maximum range at which we were operating during this effort. And it was so cool because we got to spend a lot of time with these animals. In some cases, we were 10 or 12 miles offshore, the only boat out there, just listening to the whales as they were surfacing and blowing, coming up around the vessel near where we were operating. It was great. And we're really excited about the ability of using our equipment as it is today to pretty reliably detect those animals, and that can enable vessels to avoid hitting them. That's a huge topic in a lot of areas right now, one of which is in the USV world. As some of you may know, the US Navy has a couple of fairly large USVs. I showed the Sea Hunter vehicle in a previous slide. And those vessels basically need to have human observers, whether on board that vessel specifically or on support vessels, because they don't have a reliable marine mammal avoidance capability yet. And so we see 3D forward-looking sonar as a great technology to support USV operations in need of marine mammal detection and avoidance. So our equipment is installed on a wide range of vessels today all around the world: yachts, cruise ships, coast guards, research vessels. We did a temporary installation on board your vessel, the Gulf Surveyor, a couple summers ago. So we've done a lot of different things in a lot of different places. And in most cases, though every vessel is unique, they all follow our same basic installation concept, which is integrating a fairing to the hull, and that fairing is essentially a tube, and then installing the sonar transducer module into the front of that tube facing forward. Every vessel is pretty unique, but the concept is pretty much the same. And here's a couple of examples of that fairing tube integrated into a hull. In these cases, the sonar is completely exterior to the hull because that fairing has a watertight gland going up above the waterline, and it can be installed directly on the center line, like we see here in these examples. It can be installed on a bulb. It can even be installed to the side of the hull, side of the center line, or even on a hoist. This picture here shows the hoist installation on board the RSS Sir David Attenborough, which is a full ice breaker. And when the sonar is retracted, they can crunch through multiple meters of ice. And then when they deploy the sonar, they can see ahead out to 1,000 meters ahead. It can be installed on composite hulls as well. Here's an example of a refit with the Argos 350 that goes into the fairing tube there. Most of our vessels use some variation of this concept, a fixed installation with no moving parts. However, many of our smaller USV applications have been installing our equipment on a hoist. I showed a picture before of a large hoist on a large vessel. This is a rendering of the hoist that's produced by a company called C4R based in Denmark. And they've utilized this hoist on a number of mid-size USVs, about 14 meters in length. These were all high-speed, interdiction-capable vessels. When going high speed, they retract the sonar, but when going at slower patrol speeds, they lower the sonar to navigate the vessel and also help them build the map of the areas where they're patrolling. So when they do have to interdict at high speeds, they know where to go safely. In these cases, when the transducer module is retracted, you can even have a fairing at the bottom of the transducer that matches the shape of the hull. So there's no hydrodynamic impact on the hull itself. At the end of the day, really our equipment is about enabling safe access to various locations for all types of vessels. And in this case, USVs are a great application for forward-looking sonars. It gives them access to operating in shallow waters, especially if they're poorly charted or if there's obstacles in the water column, obstacles that might change. At the end of the day, it's really about reducing the risk so that you can have an improved ROI on the vehicle. It's clear that keeping your vehicle in operation safely longer has strong economic incentives. So really, we're about how to save money operationally by keeping your vehicles on scene, in operation more safely. So I know that was a lot of information in a relatively short time. I'd be happy to take any questions that any of you may have, both there in the classroom and online. No questions. I take that to mean I either did a fantastic job or an awful job. I hope the first. If you do have questions that come up in the future.
There was a question.
Oh, we got a question. Great.
Yeah.
Yes.
Sorry, we were muted, I think.
Ah.
Great talk. Thank you very much. I had a question about limiting the scope of the forward-looking echo sounder. You talked a lot about actually seeing the seafloor, but what if, say, you were on a USV and you had limited bandwidth and you just wanted to limit what you were looking at to the draft of the USV or a little bit extra? Does that make sense?
That's a great question. So we see a couple of different use cases with the equipment on board USVs. At one end, it sounds like you're talking about a human in the loop display. So you could use our software and just do a video connection through whatever internet access you have. Alternatively, you could write your own little app that connects to our network interface and provides a much lower resolution image, or like you said, just provides information from a subset of the field of view of the sonar. Or in the third case, you could take just the LHM, that local history map, and share that, not at the video level, but at the gridded bathymetric level. In that case, you're talking at about 50 kilobits per second in nominal water depths in many cases, in that order of magnitude. So it really depends on how you want to access that data remotely. However, some of our users are interfacing their vehicle control system directly into the network interface, so that when operating in autonomous modes, their vehicle can look at essentially the point cloud, the XYZ relative to the vessel, and say, is there an obstacle in front of us? What decision should I make? Oftentimes fusing that with the AIS information, camera machine vision information, and radar information, all going into the vehicle control system in that autonomous or semi-autonomous modes.
Awesome, thank you.
Well,
Hi, Matt. It's Val Schmidt. Thank
Hi,
you so
Val.
much. Thank you so much for this talk. It's great. There's a lot of fascinating stuff in here.
Thank
I'm
you.
curious, can you see lobster pot floats?
Generally, no. That's a pretty hard target to see. I'm not aware of any system that's able to detect them at any significant ranges. We are doing some work with a survey service company that is very particularly concerned with FADS, fish aggregate devices. They are operating with both cable layers and seismic survey streamers. And where they're operating, there's a ton of illegal, unregistered FADs so they don't know where they are. They're not marked at the surface, but they can cause huge entanglement headaches. And they've been using our equipment to do some FAD detection. But of course, that's a much bigger object and a much bigger reflector than just a small lobster pot buoy.
I have one follow-up question, not related to lobster pot buoys, but obviously sometimes in the summer you can get a thermocline that would severely restrict your range capabilities and sort of drive all the sound energy into the seafloor maybe. And I'm curious, do you have a way to sort of warn operators that the effective range may be shorter than they realize?
Sort of. So we have vessels operating in really warm places around the world, Middle East, Southeast Asia, and so forth. Currently, we assume a isovelocity sound speed in our software, which we know is not true. And what we found is in most cases, most of the effect is you get a downward refracting environment, and that causes the seafloor, instead of appearing flat, to actually pull up more shallow with range. And so we're actually producing a more conservative view of what's ahead than if we were fully correcting for the sound speed profiles. Having an automated range of the day is something that we have started to look at. What we've found that in most cases, our equipment is fairly well over-designed so that they're not getting any significant maximum range hits between cold water and warm water. What this means is we could probably go farther in many conditions than what we are performing out to, but we haven't really pushed the limit there yet. And on the topic of sound speed profile corrections or hydrographic survey applications, once the data is input into the QPS ecosystem, you can apply sound speed profile corrections inside their ecosystem for more accurate renderings of the seafloor.
Cool, thank you.
And then one last topic regarding sound speed. We do have a patent that's recently been issued in a number of countries and soon to be issued, hopefully in the US, on actually calculating the refraction through the sensor as the vessel moves, that basically gives you the equivalent refraction to the seafloor from the forward-looking sonar information. It's not very helpful for looking for where is the thermocline, so biological sciences would not really benefit from it to find where's all the bait hanging out. But from the hydrographic survey point of view, it would allow you to reduce or even get rid of CTD casts in water depths where the sonar is able to detect the seafloor. That's not yet a product that we've released, but we've built some prototypes and got it far enough along that we've had patent filings on that and issued in some nationalities already.
Hello, Matt. That's a really cool application. I totally understand where you're coming from. My questions are three. The first is, I might have missed it, but what frequency is this system?
Our systems operate around 61 kilohertz approximately. They do have some bit of a frequency band, but it's fairly narrow band compared to like a wideband chirp sonar.
Okay. And is there an opportunity to store the full time series at each pixel?
We do that all the time from our engineering point of view. That's not part of our typical end user product because they're not looking to reprocess data. But whenever we go out for our own engineering testing, we're recording all raw signals coming into the sensor. This allows us to reprocess with new algorithms and new techniques. To date, we have about 80 terabytes of data collected around the world from various vessels and various sonars in various conditions. We have about another 60 terabytes of drives in the field with some of our customers recording raw data. Before we had this cloud service to share the gridded data across the fleet, we were doing it the old-fashioned way by sending out USB drives, having our customers record raw data, sending it back to us, and then we would process and send it to the IHO's database. We're still doing that to some extent, but we're trying to accelerate the bathymetric collections by focusing on the cloud service with that gridded aggregate product.
Thank you. My last question is, how much does this thing cost?
The Argos 350, the shortest range, has a list price of about $57,000, and the longest range product, the Argos 1000, I believe is $184,000 list price.
That's pretty cheap. Thank you. That's awesome.
I do have a question. It's Daniel here. So what's the smallest object that you can resolve? My question is, why I'm asking you that, it's because a few years ago I was in Greenland and we hit a small iceberg. But it's a small one that you cannot see it, it's quite clear from the surface, but it's big enough to damage the propeller, and that's what's happened. That's why I'm asking you that. What is the smallest object that you can resolve?
Well, it's a function of how big it is acoustically, not how big it is physically. Ice is a great obstacle, a great reflector, and we have a lot of vessels that are ice classed, both in the Arctic and the Antarctic, that have our equipment on board specifically because they want to avoid those types of growlers, bergy bits. If it's big enough to damage the vessel, it's big enough in general to be detectable by the FarSounder systems on board. We have our systems installed on about 12% of the expedition cruise ship fleet. So those are the smaller cruise ships that are doing Northwest Passage, Greenland, Antarctica. We are not required equipment, but they're buying our equipment because it's clear to them that it helps let them navigate more safely. We also have a number of yacht customers that are ice classed going to those same locations, and a number of research vessels that are also operating in those areas.
Thank you. I think there is a online question, right?
Yeah, so Guy Knoll asked, what format is your data contribution to NCEI, and do you also export to GSF? So I'll start with the NCEI question first. We are working out those details right now with Georgie and Jennifer Jenks. We've been contributing echo sounder measurements to the DCDB, and we are a trusted node of the DCDB using their standard formats. I think the format has mostly been decided for the local history map, that gridded data, and we're just waiting on the formality of getting the signature signed before we can start pushing data in real time to the NCEI. What that format is, I have absolutely no idea. My colleague Keith has been mostly working on that, but it's something that is well documented. As for GSF, that's not something that we currently do, but it is certainly something that we could do if there was a need and a customer application for that.
Any other questions?
I have a follow-up question.
Yes, Paul?
Matt, do you have a sense of what kind of penalty you pay, say at a nominal speed of maybe 8 or 10 knots in terms of flow noise and to the noise floor of the system?
That's a great question. It depends a lot on the vehicle itself and the particular installation design. And I don't have a single quantitative number that I can give you. What I can say is our Argos 1000, the longest range mode sonar, is designed for operation up to 25 knots. The reason for that is the signals we use are fairly Doppler tolerant, so we're not doing any real-time Doppler shift corrections. And after about 25 knots, we're not matching the signals transmitted to the signals received so well, so we start to lose some match filtering response there. We could do dynamic Doppler shift matching. We haven't bothered to do that yet because we haven't needed to. And I've been on board one of our customers' vessels at 32 knots, and the system still worked quite well. Having said that, I've been on other vessels of ours, customers, at 18 knots, and the system worked poorly. In those cases, it was a vessel with a lot of mechanical engine noise and vibrations, so much so that when you're standing on the bridge, your feet are almost numb from the vibrations through the deck. So it really comes down not so much to the flow noise, but the mechanical vibration and acoustic noise generated by the engines through the hull.
Thanks.
Anyone else?
Yeah,
Yes.
one more. This isn't a question. Matt, hi Matt, I'm so happy to see you. I'm happy to see how FarSounder has become successful. I don't know if you remember 20 years ago, I worked at MSI when you were just developing the transducers.
I'm sorry, I don't know. I see the back of your heads. I don't know who you are.
You haven't seen me for over 20 years, but I was there with Brian Pazol at MSI, when you were first starting out making the transducers, and now
Yep.
It's really cool to see how successful your company is and that you're.
Thank you.
That's great. Good to see you. I was hoping to see you here in person.
I appreciate that. Yeah, I'm sorry I couldn't make it in person. I was on the road 2 weeks of the last 4, and I leave again tomorrow for another 2 weeks this month. So I just, my family would divorce me, I think, if I spent another day away from them. So unfortunately, I couldn't make it.
Well, great talk. Thanks very much.
Thank you.
Okay, I think that's all. Thank you so much. And
thanks, everybody. Have a great day, and feel free to reach out on LinkedIn, social media, and so forth, or send an email if you have any other follow-up questions. Thank you.
thank you, Matt.